Linear algebra mastery. Welcome back, everybody. Now, we will jump into Anki to begin with, as usual, because we gotta check if we have any flashcards due. Nothing is due? Okay, then what did we learn yesterday? All right. We're getting pretty advanced here. I'm learning quite a lot here. What did we learn about yesterday, though? Man, oh man, what did we learn about yesterday? Gaussian. We learned about Gaussian elimination. Yes. We learned that the algorithm I learned how to calculate or how to get a matrix into reduced row echelon form and row echelon form, right? To get row echelon form, that is called Gaussian elimination, at least the algorithm we learned. And to get it into reduced row echelon form, that's Gauss-Jordan elimination. Okay. Basically, Gauss-Jordan elimination has a forward and a backward phase. The forward phase is eliminating the digits, the non-zero digits below the leading ones, and the backward phase is eliminating the non-zero digits above the leading ones. Right? Gaussian elimination is just the forward phase of the Gauss-Jordan elimination method. We learned a little bit about what was his name? Carl Friedrich Gauss. People had done Gaussian elimination before, but he popularized it, and so we call it Gaussian elimination. And Wilhelm Jordan further popularized the method in his book on geodesy, calculating the sizes and shapes of earthly objects, something along those lines, geodesy. And Gauss, he popularized the method when he calculated or he predicted the orbit of an asteroid pretty accurately in the 1800s. Okay, so that's a little bit of historical note. Then we looked at actually doing a Gauss-Jordan elimination example. Right, then what would we have done after that? Okay, we started looking at homogeneous linear systems, which we learned in chapter 1, section 1. That's just basically when the constant, the b in the linear equation, is equal to 0. And we talked a little bit about the nature of homogeneous linear systems, in that since they have the b being 0, there's always going to be at least one solution for homogeneous linear systems. And that is called there's a term for it. It's where all the variables just simply equal 1, or equal 0, I mean. So 0 equals 0. It's called the something type of answer. The trajectory, implicit, no. Simple, no. Anyway, there's a term for it. We'll get that term in a second, for when all the variables simply equal 0, so it's 0 equals 0. So all homogeneous linear systems are consistent because they have at least one solution. If there are more than one solution, you're going to have infinitely many solutions. And there's another term for these solutions that are not when the variables are simply equal to 0, which we'll get right now. All right, checking what we got. Cool. Yep. Yes, got it. Okay. Yep. Trivial solutions. I knew it started with a T. I knew it was like a simple trivial solution. The trivial solution. All right, that's when all the variables simply equal 0 in a homogeneous linear system. And then the other ones are called, you guessed it, non-trivial solutions. All right. Yep. So it really has only two possibilities for solutions for homogeneous linear systems. You got either one trivial solution or you've got infinitely many solutions, one of which is a trivial solution. All right. Now I'm going to continue reading, and then I'll be back to recall in a sec. All right, just finished up the section called homogeneous linear solutions. Last things I learned from this section are that when you've got two equations in a linear system with two unknowns, and they're homogeneous, it's a homogeneous linear system, or homogeneous, then and they only have one solution, meaning the trivial solution, that point of intersection is at the origin. Cool? All right, and the other thing is, you know that there's a time where you're guaranteed to have infinitely many solutions, meaning you have non-trivial solutions in a homogeneous linear system. When is that? Well, when you have more unknowns than equations, you're guaranteed to have infinitely many solutions. Cool. I summarized this section just by saying, like, homogeneous linear systems are always consistent due to always having at least the trivial solution. All right, so the next section is called free variables in homogeneous linear systems. So that's what I'm going to start reading, and I'll be back to recall that. All right, I'm brain fried after that. Basically, this whole next section, free variables in homogeneous systems, linear systems. This was all about proving, I'm just going to write this by what the section was about, proving that homogeneous linear systems with more unknowns than equations have infinitely many solutions. All right, wow. So basically, from the example before, in the last section, we did an example of solving a homogeneous linear system with more unknowns than equations. We gained some valuable insights. First of all, an augmented matrix will always have the same amount of equations of the corresponding linear system or greater, because when we have a row of zeros, that basically just equates to 0 equals 0, and that it doesn't have any implications on the unknowns, so we can ignore it in the linear systems. So there's always going to be more rows or equal rows greater than or equal to the number of linear system, or the linear equations in the system, okay? There was something else. Right. Elementary row operations do not affect columns of zeros. So if the rightmost column is all 0 in an augmented matrix, then it's a homogeneous linear system. You won't be able to change that with elementary row operations. Okay? Now, we get into proving why all homogeneous linear systems that have more unknowns than equations have infinitely many solutions, okay? So basically, we can say that we're talking about linear or leading ones or leading variables and leading variables and free variables. If you have free variables in a homogeneous system, you're going to have infinitely many solutions, but that's not the proof. The proof first puts out the form of basically a linear system, a homogeneous linear system in n unknowns and r solutions. R equations, I believe. R equations? No, it wasn't R equations. It's n minus r. What is r? Oh, what is r? The number of free variables. No, the number of leading ones, right. So basically, by definition, if you have n, which is the number of known unknowns, if n is greater than R, which is the leading ones, then you're going to have free variables, just by definition. And free variables mean infinitely many solutions in a homogeneous linear system. Okay. How do you know you're going to have more free variables? Well, basically, you say if each equation has one leading variable at the max, you can't have more than one leading variable. Like, you can only have one leading one. So you can only have one leading one per equation. So this is the second theorem that proves it. It's basically like, so if you have more equations if you have more unknowns n than equations m, you're going to also have more unknowns than leading variables, which means you, by definition, you have at least one free variable. And if you have any free variables, you're going to have infinitely many solutions. All right, I'm just going to keep recalling. This only works for homogeneous linear systems, but we will prove in the future that if you have a consistent non-homogeneous linear system that has more unknowns than equations, then you're also going to have infinitely many solutions. Okay, what am I missing? If a homogeneous linear system, what was this about? If a homogeneous linear system has n unknowns and the reduced row echelon form, that's what I forgot. Reduced row echelon form is its augmented matrix has r non-zero rows. Right, it can't just be rows, it's r non-zero rows. It's non-zero rows. Okay. So this first one is basically just how to determine how many free variables. It's the theorem of how to determine how many free variables you got. Basically, in a homogeneous linear system with R being the number of non-zero rows in its reduced row echelon form of its augmented matrix, and n being the number of unknowns, the number of free variables in the linear system will be n minus r. Cool. This is just basically how to calculate the number of free variables by definition. In a homogeneous linear system. So that's just about finding the number of free variables. And then basically the second theorem is saying if you've got free variables, it's going to have infinitely many solutions in a homogeneous system. A homogeneous linear system with more unknowns than equations has infinitely many solutions. All right. I think we got the point of how to prove it, the general gist of proving that homogeneous linear systems with more non-zero equations. With more homogeneous linear systems with more unknowns than equations. Non-zero equations, but just that doesn't non-zero rows, but so just equations. More unknowns than equations have infinitely many solutions, and we talked about how to prove that by definitions and theorems. I have not done a ton of work with proofs in my life, so it makes sense about proving, but I'm still new. All right. There we go. We are actually very close now. That was a dense page. But we were very close. We got Gaussian elimination and back substitution as the next section. Some facts about echelon forms. That's a super short one. And then even shorter is round off error and instability. So we got 3 sections left. 3 smallish sections until we're into the practice problems. So, cool. Working with proofs. We're getting into it now in this next practice set. So watching those videos on the website about, what was it called? how to read and do proofs will probably be very beneficial. All right, that's it for today. Talk to you guys later. See you.